Hello everyone! This video is entitled Periodic Trends. Periodic trends are specific patterns in the properties of elements within the periodic table. These properties affect how the elements will react with one another, and thus they explain why elements in a particular group react similarly. It is for this reason that groups are called families on the periodic table. In this video, I will be covering periodic trends that relate to atomic radius, ionization energy, and electron affinity. The information presented here is not only important, but will be incredibly helpful when trying to understand ideas including reactivity and compound formation. Okay, let's get started. The first trend I'm going to cover in this lecture is that of atomic radius. Before I describe this trend, I think it's important to review the definition of radius.
The radius of a circle or a sphere is the distance from the center of that circle or sphere to its outer ridge. More specifically, the radius is half the diameter. So obviously, as it relates to an atom, atomic radius is the distance from the nucleus of a particular element to its outermost energy level. There are two general trends for atomic size. One trend relates to the groups on the periodic table, and the other relates to the periods moving across left to right on the periodic table. Both of these trends are caused by different amounts of attraction and repulsion electrons feel in each atom. As you go down each group in the periodic table, the size of the atoms increase. The lower in a group you go, the further the valence electrons are from the nucleus. This results in an outer electron sensing less attraction to the nucleus, which is due to a phenomenon we call electron shielding. Electron shielding is exactly what it sounds like. As you can see in the image to the right, although the outermost electrons of the atom still feel the attractive pull of the nucleus, the electrons in the inner shells push the valence electrons out due to repulsion. Now it goes without saying that the more shells there are between the nucleus and the valence electrons, the greater repulsion they will feel due to the electrons in the lower energy levels. So, as you go down a group, you're increasing the number of inner shells there are between the nucleus and the valence electrons. This thereby causes the atom to grow in size due to an increased sense by the outermost electrons of repulsion and a decreased sense of attraction to the nucleus. As you go across a period, left to right, the size of the atom decreases. This is caused by an increase in the positive charge within the nucleus. As you move across a period, the number of energy levels remains the same, but the number of protons within the nucleus increases. This results in a greater positive force exerted by the nucleus on the same number of energy levels within the particular period. So, if you were to compare sodium, which is to the far left of the periodic table, to chlorine, which is on the far right, you would find that chlorine is much smaller in size. Even though both sodium and chlorine have electrons in 3 energy levels, sodium only has 11 protons to pull its electrons in, whereas chlorine has 17. It is for this reason that chlorine's electrons are closer to its nucleus, and the atom is smaller in size. So to review, as you go down a group on the periodic table, you're increasing atomic radius. As you go across from left to right on the periodic table, you're decreasing atomic radius. It's important to note the relationship between atomic radius and ionic radius. To review, an ion is the charged form of an atom when it gains or loses an electron. A cation is a positively charged ion that occurs when an atom loses an electron. An anion is a negatively charged ion that occurs when an atom gains an electron. Now, what's interesting about the radius of an ion is how it's different in size from that of the atom it came from. When an atom gives up or gains an electron, the size of the ion that results is different from the size of the original neutral atom. More specifically, the ions of metals, which tend to be cations, are smaller than their corresponding neutral atoms. And the ions of nonmetals, which tend to be anions, are larger than their corresponding atoms. Although this may sound a little confusing, it's actually quite simple to understand. When an atom loses electrons to become a cation, it resultantly contains a greater number of protons than it does electrons. This imbalance causes the remaining electrons to be drawn closer to the nucleus. Thus, the radius of the cation is less than its parent atom. However, when an atom gains an electron to become an anion, it resultantly contains a greater number of electrons than it does protons. This imbalance causes the electrons to experience less pull towards the nucleus, and thus the radius of the anion is greater than its parent atom. This image on the right shows the relationship of ions to atoms, where a positive ion is smaller than its atom. A negative ion, in the case of chlorine, is larger than its atom. The next trend I'm going to discuss with you is called ionization energy. Ionization is the word used to identify the process by which an atom becomes an ion. Now, I know we've already gone through this, but it's important to solidify this point. All atoms are neutral by nature, and this is because they contain the same number of protons as they do electrons. In their neutral states, atoms are unstable, with the exclusion of one group on the periodic table, noble gases. To become stable, these atoms will lose electrons or gain electrons to become either cations or anions respectively. Atoms will do this so that they can have the same stable arrangement of electrons, just like those in noble gases. When the electron configuration in an ion exactly matches those of a noble gas, that ion is said to be isoelectronic with that noble gas. It is important to remember that every single atom loses or gains electrons so that it can ultimately become isoelectronic with the closest noble gas, the noble gas that has the closest number of electrons. Now, of course, to become an ion requires energy. Energy is required whether an atom is having an electron removed or it is removing an electron from another. It is important to understand that each electron is pulled into the nucleus of an atom by way of attractive force. So, for an atom to remove an electron from another, it must overcome that attractive pull the electron is feeling from the nucleus. This energy that is required to remove an electron from an atom is called ionization energy. And obviously, if an atom cannot overcome the ionization energy required to steal an electron from another, then ionization does not occur. When trying to determine whether an atom has a high or low ionization energy, you must first consider whether the atom wants to gain electrons or lose electrons. If an atom wants to lose electrons to become stable, it obviously will not require as much energy to remove those electrons the atom is trying to get rid of. However, if an atom is trying to gain electrons to become stable, then it will require an incredibly large amount of energy to take the electrons it has within its outer energy level. This concept is analogous to food and hunger. If you've just eaten and you have an extra sandwich you'd rather not carry around with you, then obviously you'd be more than happy to part with it. But if you're starving and the sandwich you have is not enough to satiate your hunger, then you will of course put up a fight to keep it. The bar graph to the bottom right shows the group 1 metals ranging from lithium to cesium having relatively low ionization energies. This is because these metals want to lose electrons. it takes relatively small amounts of energy to remove the electrons from these atoms. The nonmetals, like neon, fluorine, and oxygen, have relatively high ionization energies. This is due to the strong attractive force pulling down on the valence electrons. Due to the ratio of positive to negative force, these nonmetals hold on to their electrons and try to gain more electrons to become negative ions. Now, of course, it is possible for certain elements to lose more than one electron to achieve a stable electron configuration. The energy required to remove one electron from the valence energy level of an atom is called the first ionization energy. The energy required for every subsequent electron would be called the second, third, or fourth ionization energies, respectively. This table shows the successive ionization energies for period 3 elements. The first column on the left has the ionization energies numbered 1 to 7. The values for the ionization energies in the first row of this table are justifiable when you consider the stability of each element. The values for sodium, magnesium, and aluminum are all relatively low due to a need to lose electrons to achieve a stable state. Silicon's first ionization energy is also somewhat low because it can gain or lose electrons to reach a stable state based on its position on the periodic table. However, the values for phosphorus, sulfur, and chlorine are all quite high due to a need to retain the electrons they have and gain additional electrons to achieve a stable state. The ionization energy for argon is the highest in this row simply due to the fact that it's a noble gas and already has a stable electron arrangement. If we jump to the second row of values, you'll see that the numbers are quite different. The second ionization energy for sodium is more than 9 times as high as the first ionization energy. This is of course explained by the mere fact that sodium wants to keep the remainder of its electrons because it has reached a stable electron configuration. By losing the only electron it had in the third energy level, it is left with a filled second energy level, which is incredibly stable. If sodium were to lose any more electrons, it would become extremely unstable, and thus its second ionization energy is very high. It is important to remember that when an atom loses an electron, the resultant ion will have more protons than it does electrons. This creates a greater positive attractive force from the nucleus, which acts to pull the electrons towards the center of the atom more. And so, if you look at the second ionization energy for magnesium, although magnesium wants to lose a second electron, which would leave behind a full second energy level, the value of its second ionization energy is quite high. This is of course due to the fact that a greater positive force of attraction was created when magnesium lost its first electron. It now has more protons than it does electrons, which makes it more difficult to remove the second electron. This pattern repeats as you move across the table or you move down the columns of this table. The elements that do not want to lose any more electrons will hold on to the remaining electrons with even greater force, and the elements that have reached a stable state will make it near impossible to remove another electron. There are two general trends for ionization energy on the periodic table. As you go down a group, the ionization energy decreases. This is of course justified because the electrons in the outer energy level are farther from the positive force of the nucleus, and thus they are easier to remove than electrons found in lower energy levels. As you go across a period, the ionization energy increases. This is explained by the increase in number of protons in each atom as you move from left to right on the periodic table. Although the elements in a particular period have the same number of energy levels, as you move across a period, each element will contain more protons to pull the electrons inward to the nucleus. This makes it more difficult to remove an electron from an atom, thereby increasing its ionization energy. Noble gases have the highest ionization energy of all the elements because they are incredibly stable, and of course they do not want to lose electrons. So to review the trends for ionization energy, as you move down a group on the periodic table, ionization energy decreases. As you move across a period on the periodic table, ionization energy increases. Electron affinity is the last periodic trend I will be discussing in this lecture. Electron affinity is a measure of the energy change associated with an atom gaining an electron. In most cases, electron affinity is a negative value, which means that energy is released in the process of adding an electron to an atom. This of course makes sense as most atoms become more stable with the addition of an electron. However, there are exceptions where the electron affinity is a positive value. This occurs in cases where an atom becomes very unstable upon receiving an electron. The more negative the electron affinity values, the easier it is to add an electron to a particular atom, and the more stable it becomes as a result. The more positive the electron affinity values, the harder it is to add an electron to a particular atom, and the more unstable it becomes as a result. There are two general trends for electron affinity on the periodic table. As you go down a group on the periodic table, the electron affinity tends to decrease, become more positive, due to a greater amount of electron repulsion brought on by a greater number of filled inner energy levels. But as you go across a period on the periodic table, the electron affinity values become more negative due to the greater atom stability that results when an electron is added. So to review the electron affinity trends, as you go down a group on the periodic table, electron affinity decreases. But as you go across from left to right on the periodic table, electron affinity increases. Here we can see how these three periodic trends increase and decrease together along the periodic table. It's important to bear in mind that although one periodic trend may be decreasing while the other is increasing, they're doing so very likely for the same reason. For example, if you take a look at the decrease in atomic radius is decreasing because of an increase of positive force in the nucleus. The more protons you add to a nucleus, the closer the energy levels are pulled in, thereby shrinking the atomic radius. It is for that exact reason that the ionization energy increases going from left to right. So here we're going to review some of the key points from this package. Atomic size has trends that are the reverse of ionization energy and electron affinity. Groups 16 and 17 elements attract electrons strongly, and so because of this, they have high ionization energies and high electron affinities. Remember, they need electrons to reach a level of stability. Group 1 and 2 elements give electrons up easily, and so because of this, they have low ionization energies and low electron affinities. They're trying to get rid of electrons to reach a level of stability. And of course, noble gases do not attract electrons, so that gives them very high ionization energies and very low electron affinities. They've already reached a level of stability. And so with that, we conclude this package and this lecture. I hope you understood everything I discussed today, and thank you for listening, and have a good day.